This is the second lecture of the Radar Systems Engineering course, and it's a review of electromagnetism. There are a number of students who are taking the course and who wish to take the course who have not had a third-year undergraduate course or better in electromagnetism. Many of them are, say, electrical and computer engineering majors who have gone down the computer engineering track, CS majors, math majors, mechanical engineers. This is a very brief, the order of magnitude of an hour review of the electromagnetism that you'll need to understand reasonably well to take this course. The electromagnetism that you'll need is really focused in a number of the sections of different lectures. You still get but you really need a good background in electromagnetism. So we're going to move on with that, and you should take a formal course or a course on the web or something like that if you haven't been exposed to an advanced undergraduate or a graduate course. Of course, that would be best in electromagnetism. First, I'm going to introduce this subject by very quickly going over the 5 different key laws and that all highlight and coming together as Maxwell's equations, and then study, and we're not going to study electrostatics and magnetostatics. We're going to study time-varying electromagnetic waves, because that's what microwaves are. And I'm going to focus on the points in time-varying electromagnetism that are important and that will be bearing on as we study particularly the antenna lectures and the radar cross-section lectures. Now we move on to the first of the laws, Coulomb's law, which states that if 2 electric charges, Q1 and Q2, are separated by a distance r, then they experience a force, and that force is given by the magnitude of the first charge, the second charge. The force, which is a vector, is along the direction between the 2 charges, divided by epsilon 0, which is the permittivity of free space, 8.85 times 10 to the minus 12 in these units, and divided by r squared. And note that the 2 charges, if they're of opposite sign, they attract, and 2 charges of the same sign repel each other. The magnitude of the electric force is proportional to the magnitude of the 2 charges and inversely proportional to the distance between the 2 charges. And the force is along the line between the 2 charges. And here is a photograph of Charles Coulomb, and you can see about when he did his work. Now, the concept of electric field, and here's where I had my mistake. I had an R here, not an R squared. The electric field is really, in physical terms, it's the force per unit charge. So if I want to know the electric field, the distance r away from a charge Q1, it's just the force divided by a unit charge at point P. And this is that equation. It's a vector, which means it has direction and a scalar quantity. And so we have a little equation here. Force is the charge times the electric field. And here's that equation we had on the previous view graph. And then you want to understand linear superposition that vectors have. It's this property in Maxwell's equations, not in Maxwell's equations, but of all the vectors, is that the total electric field at a point in space is the sum of the electric fields of each of the different point charges, if we were dealing with point charges. And here we have the electric field of a point charge. The vectors come in towards the point charge, and if they're positive, they go outward. So if you had another charge Q out here or here, it'd be a if you had a charge here, it'd be a repulsive force. Now I'd like to define the electric flux density, and that's equal to the permittivity of the medium. In this case, we're talking free space, times the electric field. And from that, Gauss, here's a picture of him, found out and measured that this electric field density integrated over a closed surface is equal to the charge that's enclosed. And that charge, you can find out, could be a volume distribution integrated over a volume. Okay, so the volume charge density here is rho. And if you integrate the electric flux density over a closed surface, it'll give you the charge that's enclosed in the surface. And it could be a collection of charges or what have you. Cast using vector calculus, which I said we're going to need because I'll be going back and forth. Gauss's law may be cast in its differential form. The divergence of the electric flux density is the charge density. And if you're curious about, do I know enough to carry on, say, go from here to here, using these two equations, using vector calculus, and see if you can handle that. For the magnetic field, Biot-Savart developed this law, which describes the magnetic field that's generated by a steady current. And that's the differential magnetic field is the current divided by 4 pi times the steady current that flows through a differential length crossed into a unit vector along the line of the current element located to the measurement position that you're measuring the magnetic field density, and divided by the distance between the DL and the measurement point R. And for an ensemble of current elements, you just integrate this up, and here's the formula for the magnetic field intensity. Now, with regard to magnetic field, and this statement could be, say, it's Gauss's law for magnetism. If it states that there are no magnetic charges. That is to say, if you integrate over a closed surface the magnetic flux density, what you'll get is 0. And that implies that in differential form, the divergence of the magnetic field is 0. That says there are no magnetic charges. And if you could find the magnetic monopole, which this would mean if there were magnetic charges, if you could find a magnetic monopole, then you get a Nobel Prize. There are dipoles. The Earth is a dipole. You can put charge on a magnet. There'll be one side north, the other side south. You integrate over the closed surface, and you'll get a dipole. You won't get a monopole. The magnetic field lines always form closed, continuous paths. Otherwise, there'd be magnetic sources, and they'd exist. And now on to Ampere's law for constant currents. If a closed contour is bounded by a surface, then the path integral over that closed contour of the magnetic field, the line integral, is equal to the surface integral over that surface. And that's the surface current density. And that's equal to the current. And its differential equivalent is that the curl of the magnetic field is equal to the current density. And the directions of the sign rule between I and H is they obey the right-hand rule. The line integral of H around a closed path C is just equals the current moving through that surface bounded by the closed path. Now, Faraday's law says that a changing the magnetic field induces an electric field. And it's stated in integral form in this equation and in differential form in this equation. So if you have a magnetic field that changes in time, you'll get an electric field. And induced electric fields are determined by minus dB dt, and magnetic fields are determined by magnetostatic, are determined by mu0 in a vacuum times the current density. Okay, now on to Maxwell's equations. If we take those first four equations and put down the relationships, I don't have mu0 or epsilon 0 because epsilon is the permittivity of the medium and mu is the permeability of the medium that you're talking about. Surprise, these formulas are inconsistent. If we go through the first, the inconsistency comes about from a well-known property of vectors that the divergence of the curl of the vector is equal to 0. And that you can prove if you've taken a course in vector calculus, you can work out the details yourself. If you apply this to Faraday's law, the left side is 0 because of the above properties, and the right-hand side is 0 because the divergence of the magnetic field is 0. But if you do the same operation on Ampere's law, we have trouble. The left side is 0, but the right side is not generally 0. If one applies Gauss's law and the continuity equation, this is the continuity equation, you get this formula. If you apply Gauss's law and the continuity equation, you get the divergence of the current density plus the rate of change of the charge is 0, which means that the current density flowing out of a volume is equal to the rate of change of the charge density leaving it. And what that added in here says is that there's an extra current. See, this is epsilon 0 dE dt is really dd dt. And so that Maxwell's equations become consistent if we rewrite that the curl of the magnetic field intensity is the current plus the rate of change of the electric field flux density. So a changing electric field induces a magnetic field and vice versa. And this is the part, now if we add this dd dt term to Maxwell's equations, we get this form. See, here's that extra, and this is called the displacement current. And Maxwell realized that you had to do this to have consistency in the equations. And here are Maxwell's equations in integral form and differential form. And for a plane wave solution with no sources, vacuum, and here we see a plane wave transmitting out field, magnetic field in red. The distance between the peaks is the wavelength. And so we have here a magnetic field along the x direction and the electric field in the y direction. And if we run the if we cross E into H, we get the direction of the electromagnetic wave that moves out. Okay, now on to boundary conditions. If we use the Gauss's law and we set up a mediums that are in a plane, one above and one below the plane, and we set up a little pillbox that extends through the plane, and n is the normal vector to the plane, and above, we'll say, is medium 1, and below is medium 2, with different dielectric constants they could be. Then it follows from Gauss's law that the dot product of the normal vector into the difference of the displacement vectors is the charge density on the surface. And from the fact that we have no dipoles, we have a similar expression for the normal components of the flux density in the magnetic regime and in the electric regime. So in scalar form, these reduce to the normal component in one medium minus the normal component of the flux density in the other medium is just the surface charge on these. Now we know that in an electromagnetic wave impinging on a conductor, there's going to be these fields won't penetrate the conductor. And that means that a charge density, if this electric field is changing with time, you'll have a surface charge density that varies with time on the conductor. And that means that there will be a reflection of an electric field by the induced current. A changing current here, there'll be an induced electromagnetic wave. And now we continue with the boundary equations. Before we looked at the normal components of the electric and magnetic field, and now we're going to use other of Maxwell's equations, Ampere's law, and then Faraday's law to derive boundary conditions for the tangential components of the magnetic field intensity and the electric field intensity. The surface we're going to use is again a flat surface with a rectangular perpendicular to the surface, and on one side, and it extends down below to the bottom side in medium 2, medium 1 above the plane. And here we see noted the tangential component of the magnetic field. Now, in the limit when the sides of the rectangle approach 0, Ampere's law reduces to this equation. What we're doing is we're performing a line integral around this path to find out what the current density is on the surface. And as the sides get small, we just have the tangential component here and here. The difference of those two components, if you cross the normal to the surface into the vectors themselves, you'll get the tangential component. And we do the same with Faraday's law. For a perfect conductor, these equations reduce to these and these, which basically say that at the surface of a perfect conductor, if the electric field is changing and the magnetic field is changing, we'll have changes in the current density and in the surface charge per unit area changing. And the scalar form of these equations in for Ampere's law and from Faraday's law are these. Well, I went a little bit overboard in terms of the length of what I recorded. I recorded the entire 47, 48 minutes or whatever of the electromagnetism in one shoot. So this is going to be the second half of the lectures on electromagnetism, so it'll be in two pieces. Now on to electromagnetic waves and how they're generated. Radiation is generated by time-varying currents, as I was alluding to, or the acceleration or deceleration of a single charge. And two examples are an oscillating dipole. Here's the expression for it. It's along the two charges of opposite sign whose separation oscillates accordingly. And a loop of wire which is driven by an oscillating current of this form. And either two methods are examples of where you can generate electromagnetic waves. And if we look at the case of two charges moving back and forth, which is a dipole, the distance between the dipole is changing sinusoidally with time, t being the period, we see that the electric field is going to go from the positive to the negative charge, and then a little while later, the field, the front expands, and then when it gets to the center, the field lines break from the dipole, and then this closed surface of electric field goes off and forms a closed loop, and the process moves further expanding, and it just continues out. There's a radiating pattern for the electric field. And since the moving charges generate a current, the current will be changing and magnetic fields will be generated. And these you can generate movies of what antenna radiation will look like in time via the time domain, the finite difference time domain method. And we're going to study this method in a later lecture on radar cross-section. And I'm going to show you two simple examples of one dipole and two dipoles of harmonic sources. Okay, now here is vertical distance and horizontal distance, and at this point we have an oscillating dipole, excuse me. And we see the field, the radiation, radiating out. Now if we have two dipoles, we'll see we'll get interference from them and nulls between them. And we'll study this in more detail, how these sources can amplify and form beams, a line of sources of dipoles or point charges traveling, emitting electromagnetic waves can generate beams. Okay, the part of the electromagnetic spectrum, which I think we alluded to before, is in this regime of frequencies, up here microwaves. And it shows you, it's a nice visual courtesy of Berkeley National Laboratory. This is where radar is. And this is in hertz, and this is the wavelength in meters. Size of a baseball, size of a period. Now, why do we use microwaves for radar? And it's basically for a couple of regions. The first main reason is that we want to use this particular band in particular because there's very little attenuation. There's almost 100% attenuation, and then we get reasonable attenuation. And there's only a couple of places down in the infrared region where the wavelengths are very small and it's hard to do scanning over wide areas with those. Above 10 gigahertz, there's very heavy attenuation by gaseous components in the atmosphere, except at windows at 35 and 95 gigahertz, and the other region below 3 megahertz implies frequencies that are too large to be practical. Implies antennas. The antenna will be lambda over d, the size, and you have to have incredibly huge antennas. Okay. Now, an electromagnetic wave is really just a set of electric and magnetic fields that jointly satisfy Maxwell's equations. So electric currents can be set up on metal surfaces and magnetic currents on apertures, and we can generate, by integrating over the areas of the currents and the electric currents and magnetic currents that are changing with time on these different either apertures or on metal. And the source distributions can be modeled and calculated, and the field can be calculated from these models. The electric current on a dipole wire, and here's what the electric current would look like at different wavelengths, and also a magnetic current in a slot. This is the electric field distribution. The phasor representation is used to sort of take out the sinusoidal variation in electromagnetic waves. And it's often used by electrical engineers in their dialect of discussing electromagnetism. And so if we have an instantaneous harmonic field, which is, say, the electric field's a function of x, y, z, and t, it can be described by a unit vector, and then this curly means the phasor, the magnitude of the phasor, and its phase, a complex number. And here's the representation of the phasor. The complex electric field is a unit vector, and its direction times the magnitude times the phase. So any time variation can be expressed as a superposition of harmonic solutions by Fourier analysis. Next I'd like to point out is when you're solving Maxwell's equations and you want to know what the electromagnetic field is, for distances that are much less, where the distance you're interested in is significantly less than 0.62 times the cube root of the size of the antenna over the wavelength, that would be the reactive near zone. It's relatively straightforward and to calculate this. And it's the energy stored in the vicinity of the antenna. And it's used to calculate input impedance as a mutual coupling between elements of an array of antennas that are generating one giant beam. In the far field, the so-called Fraunhofer region, that's when the range is significantly greater than twice the diameter of the radiator divided by the wavelength. All the power is radiated out, and the radiated power is effectively a plane wave. And that's what the electric field is like when we're dealing about, at the target, the polarization of the wave, the antenna gain pattern of directivity, or the radar cross-section. Because when we build an antenna back here, the targets we're looking at are so far away that these properties of the electromagnetic are in the far field region. And here, this would be for this particular cartoon would be the electric field in the plane, the magnetic field coming out at the out of the view graph, and the plane wave propagating out radially. Now here in these spherical coordinate system, you can approximate that plane wave. There's no radial component in the far field. Electric and magnetic fields, they're all tangential. They're not in the radial direction. They're only in the theta and the phi direction. So the electric and magnetic fields are in the theta and phi direction, and they go as 1 over e to the minus jk r over r. They drop off as 1 over r in the far field. And this is the calculation in the far field approximation for the electric wave and the field intensity. And for the magnetic field, there's just the difference between it and the electric field is just r cross a unit vector in the direction of propagation across the far field vector divided by 1 over this quantity eta, which I had never seen before I looked at it in an electrical engineering book, is the intrinsic impedance of free space, which is the square root of mu 0 over epsilon 0, and the constants. And you can see that these are easily related to the speed of light. And k is just 2 pi over lambda, the wave propagation constant. Let's see if it works. Now the polarization of an electromagnetic wave is defined in the following manner. It's defined as the behavior of the electric field as it propagates in time as it's observed along the direction of radiation. And so you can make 3 different general forms of polarization: elliptical and linear. Elliptical and linear, and circular is just a subset of elliptical, as you'll see, and we talk about it. If we take two different electric fields, sine waves, and offset them by a factor of pi over 2, the circular electric field, they're equal in amplitude and separated by a phase of pi over 2, you'll get either right-handed or left-handed circular polarization, depending on whether the electric field is moving counterclockwise or clockwise, and we'll see a visual of that in a moment. And when the magnitude of the components that make up the combined electric field vector are not of equal amplitude, you get an elliptical pattern. Okay? When you have just one a sine wave transmitting, it usually is transmitted either in the vertical or the horizontal direction, and the horizontal polarization is used in long-range air search radars to obtain reinforcement of radiation by ground reflection. Now here is a simple plain electromagnetic wave, and you can see there's our little cartoon working. You can see it transmitting out. Okay. Now a vertical polarization is when the electric field is vertical with respect to the Earth, and horizontal polarization is when it's horizontal with respect to the Earth, and I explained why for air surveillance radars. And over water, you'd use a vertical polarization because the background clutter is less over water. Okay. Now, the electric field components, as I said, for circular polarization are equal in amplitude and separated by a phase of 90 degrees. The handedness is defined by the observation of the electric field along the propagation direction. And you want to say, well, are you looking at it? Oh, wait a minute. The propagation direction is into the paper. That's right-handed circular polarization. Okay. And it's if with the propagation directed into the paper and the electric field is moving counterclockwise, it's left-handed circular polarization. And these are the form of the instantaneous electric waves and the phasors for each. Plane waves solution, as I've gone over before, is just this, and most electromagnetic waves are generated by localized sources and expand out into free space as spherical waves. And in the far field, this is sort of summarizing it, they can be approximated by plane waves when they hit a target and scatter back energy. There are two other quantities of physical significance I'd like to define here. The Poynting vector is the power density per unit area in the field carried by the wave, and it's just E cross H. It's an S, it's the Poynting vector. And since the E and H fields are functions of time, we really usually deal with the average power density, which is just 1/2 the real part of E cross H. That's this quantity. And for a plane wave in a lossless medium, we get this quantity, where this is the impedance of free space, the average Poynting vector. There are modes of transmission for electromagnetic waves. And the reason there are different modes is because as they travel out, you can have surfaces that, conducting surfaces, that they have to obey Maxwell's equations for. Transverse electromagnetic waves have the magnetic and electric fields perpendicular to, and the K vector, the direction of propagation, perpendicular to these others. And examples of them are coaxial transmission lines and free space transmission. And there are TEM transmission lines have two parallel surfaces. Okay. Now, there are two other modes which rectangular waveguides use, the TE mode and the TM mode. In the TE mode, the electric field is perpendicular to K. That's perpendicular to the direction of motion, and there's no electric field in the direction of motion. And transverse magnetic field is just the same as your other thing. And there are hybrid modes. And these two modes are the most efficient ones to use in rectangular waveguides, which are usually the mode of choice for transmitting along from your transmitter to your antenna, microwave energy. At low power, in the low portion of the electromagnetic, the frequency spectrum of the microwave portion, if you're dealing with those low powers, you can use the small cross-section of the coaxial cable is more prone to breakdown, so you got to be careful how you use it. And there's a dielectric losses increased with frequency. So that's why the reasons why it's only used under those conditions. But it can bend easily. And you see you've got a center core of conductor and a dielectric insulator which separates the outer coaxial conductor, which is a magnetic shield usually sheathed back and forth, and then over it with a plastic jacket that would protect this coaxial waveguide, literally, with a dielectric insulator from the elements. As for waveguides, here we see a typical waveguide, and notice this one has ridged lines in it, and it is used if you have a waveguide that with these ridged lines. You can bend the waveguide so that it can make rather slight angles from one waveguide that's coming out flat to another piece that has to sort of bend like cooked spaghetti, so to speak. It has some losses in it, and we'll get into those things when we discuss transmitters and transmission lines. Metal waveguides are used for high-power radar transmission from the high-power amplifier and the transmitter to the feed, and rectangular waveguides are the most prevalent ones. And we'll go into more details of this later. Now lastly, a reason that we're very interested in electromagnetism is because we want to characterize the target. And I talked about this a little bit. The size of the target is the ratio in the limit of the distance going to infinity of the scattered electric field, the magnitude of that squared, divided by the magnitude of the incident electric field squared. And it's the effective electric area, and you can see scattering coming off this complex target in many different directions. And what a radar design is going to want to do is know where all the electric energy is going off, so you're going to have to solve Maxwell's equations and find out where that scattering is going to get the cross-section in a given direction. The cross-section varies with direction from the target. If the electromagnetic energy was impinging on the nose, it would be less than if it was impinging perpendicularly at this big scattering surface of specular, the side of this aircraft. So you're going to need to know Maxwell's equations and how to do those calculations to characterize the target. And we'll go. That's where one of the places we're going to use electromagnetism quite heavily. Now, I'd just like to add at the end of this lecture another artifact of the difference between the scientists, namely physicists, and electrical engineers. One of the things that confused me when I got out of physics graduate school is electrical engineers always talk about the differences in signal-to-noise ratio, antenna gain, whatever, in decibel units. And that's really 10 times the logarithm to the base 10 of the ratio of powers. The ratio of the signal power to the noise power, you take the logarithm to the base 10 and multiply it by 10, and that's the signal-to-noise ratio in dB. And if that would be 10 in natural units and 10 dB. If in natural units was 1,000,000, I'd say 10 to the 6th, as I was my native language. But now I think I'm bilingual. I say 60 dB also. And here's some other things to put in your cap. The simplest one is a factor of 2 is 3 dB. And you'll see as you just in time you'll know these pretty well if you come from the scientific domain. But I wanted to state it up once for definition because we'll be using it later, the dB scale. Now in summary, this has been a very, very brief overview of the electromagnetism topics that we're going to use in this course. It's a whole one-term course in advanced electromagnetism that the physicists take or their counterparts in electrical engineering take, usually in the 3rd year of undergraduate studies. The course that probably 50 to 75% of the market share in physics, there's a book by Griffiths, which is a very good book, and it's in the references. I refer to it. And also the book by Ullaby, which is the electrical engineers. Most of them take 50 to 75% of the market share. So if you want to brush up, and for another thing, the only difference in the books is Ullaby will talk about transmission lines more. He'll talk more about waveguides. There's a few pages in Griffiths on waveguides, and it's an aftermath, so to speak. And Griffiths will talk about electrostatics an awful lot, and not at all as much discussion of electrostatics, and hardly anything, if anything, on transmission lines. So if you're from one field to the other, it might be good to go back and forth. And that's one reason you'll see I assigned problems from the 2 different books, whatever might help you the most. I'd like to thank Professor Ken Chamberlain of the EE Department, UNH, for lending me his notes that he uses in department at UNH so I could see how electrical engineering is taught to electrical engineering. Okay, here are these first 2 books. And then, of course, everywhere I'm talking about things that come out of Skolnick. And these are the 2, they're the toughies. You know, I took in my sophomore year a real tough course in electromagnetism. And then we used Jackson in his senior year course. I went to MIT. It was hard. And also I took it again in graduate school in my first year at the University of Pennsylvania. And then I got it. This is a tough book. And same thing for Balanis. Only I don't think many electrical and computer engineering departments have the wherewithal to torture their students in a undergraduate course in advanced electromagnetics with Balanis. But if you're going into grad school in electrical engineering, you'll take probably this. You won't take it from Jackson. But they cover, again, with the same emphasis. And an additional book I wanted to put down is Dave Posar's book on microwave engineering, which is from my field, someone getting into radar, advanced stuff with waveguides and fields and stuff. It's a fantastic book to read and have as a source. And I refer to it later when I'm talking about transmitters and transmission lines. Fantastic book. I recommend you for your library, but not for this lecture. Now for homework, you can see I have from references 1 and 2. If you can do these problems in Griffiths, and if you have it, get from the library, Ullaby, and look at it, and you can do these, you're going to be in great shape, and vice versa. You'll see that the homework problems overlap, and they're the kind of homework problems that refer to the material I went over in the lecture. And it's important that persons who view these lectures be knowledgeable of vector calculus and phasor notation, and this problem will verify that knowledge. And I thought it up together. You just take Maxwell's equations and the continuity equation and in integral form, that the continuity equation is charge is conserved, and using vector calculus theorems, transform these 2 sets of equations to their differential form, and then transform Maxwell's equations from the differential form to the phasor form. If you can do those things, you'll understand the phasor notation and how to go between the integral form and the vector form of Maxwell's equations, and you'll have your head screwed on right for some of the sections in radar cross section and antennas where I invoke this knowledge.